between 0 and L. And time is positive, or all positive time. And here, this on the left boundary, red boundary, we have 0, so it's a 0 boundary condition. So when x is the left or right boundary. But t is good for all time. So it's a boundary condition. We can label this as our PDE for the differential equation as a boundary condition, and this will be two initial conditions. Initial condition, that is when t is 0, right? X is between 0 and L. Yeah, for both conditions. So here's the partial derivative of u with respect to t. So separation of variable, that is, we assume our solution for this homogeneous problem, right? Homogeneous because this is 0 on the right hand side. So for the homogeneous boundary value problem with these initial conditions, we will assume our solution u as a function of x and t is separable. That is, we can write the solution into a product of two functions. One is a function of x, one is a function of t. So let's call it function of x and a function of t. So if we can use this method, so since the solution is separable, then we substitute this form into the problem, into the equation. So what do we get? So here this u should satisfy the equation, right? So we substitute that u into the equation. So first you take the second order derivative with t. That will be h double derivative with t. And keep the phi in this part. So because of this, second order derivative with t. And here minus the c squared, c is a constant. C is a positive constant. So c squared times second order derivative with respect to x, right? So the u will differentiate with respect to x. So derivative. Yeah, so we just do a substitution of the form into the equation and make the 0. Okay. So still we try to separate x variable from the t variable, right? Try to separate the two variables. So then we just naturally we put all the this phi double prime. You put this to the other side. So phi double prime over phi x, and here's the h double prime and the function of t over. Okay, we can put this with function h. Okay, so they're equal. So that means we have an expression that is function of t only, right? We have the same expression is a function of x only, right? That means that it has to be a constant, right? So it has to be a constant. So then we make it equal to a constant. Certainly you can put just this ln notation, which represents a constant. But we use a negative lambda because we will show eventually this quantity is not positive. Okay, so that means a lambda will be positive. Yeah, so just for convenience, we put a negative lambda. We will prove that this lambda will be non-negative. Okay, so here we have this. What's our goal now? We have the solution in that form. We have to identify phi and h in order to solve the problem, right? So phi and h should be found. So now let's try to solve. So now after we isolated these two variables, then we just go to one equation. We get one equation of phi, second order ODE. Right, so this is the one equation of this function. And we have another equation. That's the second order ODE. So delta c square h function t. Okay, so now let's continue. So we want to determine this two. Now, from this, we substitute also that u in this form. We substitute u into the boundary condition. So we know this u should satisfy boundary condition as well. So that means at the left boundary, where from boundary condition, this phi for any time because of the zero boundary condition, right? At the left boundary, when x is 0, this is the u when x is 0. So that is u when x is L, right? When x is at the right end. So that the right boundary condition. So we should get 0. Okay, so that means if a product is 0, one of them has to be 0. If this is 0, what happens? If h of t is 0, what happens? That means u is identical to 0, right? That's just a trivial solution. We're not interested in that case. So this is a case that we're not interested, because if it's a trivial solution, it may not satisfy the initial conditions. Yeah. So that's a 0 solution. So we're not looking for that. So that means this has to be 0. So the phi at 0 is 0. And phi at L is also 0. Yeah, so we got the boundary conditions for this ODE, right? Second order ODE. And also I want to point out, for this problem, given problem, the initial conditions are known functions. Yeah, they're given. Problem, for specific problems, those are known functions. Also C is a given constant, right? Known constant. So then the problem is a very specific problem. But for this, because you realize the function f, when x is 0, f should satisfy something in order to be compatible with the boundary condition, right? Because u at the left boundary 0 for any time, it is 0, right? Even for the initial time, right? So we have to require this. The function f at 0 is equal to function at the right boundary. It has to be what? 0. 0, because the left and right boundary, no matter what time, including the initial moment, it has to be 0. So that's a condition f should satisfy because of the boundary condition. Because this should be compatible with that if u is a solution. How about g? G also should satisfy a compatibility condition. Yeah, g. So g at 0, right? G at 0, because the u at 0, it has to be 0 boundary. So when you take a derivative with respect to t, still 0, right? So that means g at 0, g at L also should satisfy the 0 boundary conditions. So those conditions are, conditions these two functions should satisfy. And we call them compatibility conditions to make the problem appropriate problem. Okay, so far we're examining the problem. We try to find a solution of this form, and then we decompose the problem into two parts. So we try to find phi and h separately, right? So this one, where we know that the phi is the second order ODE with the 0 boundary conditions. So can we try to determine the solution of this? Or if we're done with both ODEs, then we're done with the PD solution. Yeah, so we know we haven't used those initial conditions yet. But let's just do one thing at a time. So from here, how can we solve ODE? Second order, we need the, this is the ordinary differential equation with constant coefficients, right, with constant coefficients. So we need the characteristic equation, etc., to get a general solution, because this is a homogeneous, right, homogeneous, the second order ODE. So let's write the solution of this problem. So for solving this, phi okay. Remember the characteristic polynomial. If you write the polynomial, it is suppose it's a p square, right? P square. Okay, let's. The polynomial corresponding to the second order move to this side. That will be plus lambda equals 0. So this is a polynomial of p. This is a characteristic polynomial of the ODE, and we solve the polynomial. So we can look at some cases. So when lambda is negative, when lambda is 0, when lambda is positive, so we can divide it into 3 cases for the characteristic polynomial. So when lambda is negative, this is case 1. When lambda is 0, when lambda is positive. Okay, when lambda is negative, this is we have a pair of real valued solutions, right? Because p squared is positive. So p squared is positive, then p is square root of that positive number. So you have a pair of real valued solutions for the polynomial. Yeah, so in this case, what is the solution? We can find 2 independent solutions of this, right, using the roots of the polynomial. So the solution will be this form, exponential to this times x, exponential to this. So actually, remember with this exponential this or negative of this quantity, right? E to this quantity x, or e to negative of this root times x. Those are 2 independent solutions. Yeah, independent solutions. But we know if you can find 2 independent solutions, you do a linear combination, still independent solution. So actually, if you do the sum or half of this, you get a hyperbolic cosine, right? Hyperbolic cosine is also a solution. So we just for convenience, we use hyperbolic cosine, hyperbolic sine, because those are kind of symmetric form. So we use that. So for this form, we have hyperbolic cosine of this, and hyperbolic sine so as 2 independent solutions. Yeah, instead of using the exponential, just one exponential function, it's kind of, this one is a combination of 2 exponential functions, right? So they are also independent solutions. So once you find an independent solution, you can represent a general solution for the problem. So general solution of this phi as a function of x is alpha plus beta, just the arbitrary combination of the independent solutions.